Hello, today we'll be looking at section 2.2. Let's start with the average and instantaneous rate of change. So the average rate of change of a function is given by this equation right here, f of x plus h minus f of x all over h. And the instantaneous rate of change of a function f at the number x is the limit as h goes to 0 of this thing right here. We've called this before the difference quotient. Okay? So it says find the instantaneous rate of change of the temperature function f of x equals x squared at time x equals 2. So first thing we want to do is find what f of x plus h is. So f of x plus h. So you're going to plug that into this function here. So that's going to be x, instead of x squared, it'll be x plus h squared. Okay. So we know our algorithm. You double the first thing, multiply the two terms together and double them. You square the first term, then you multiply the two terms together and double them, so you get 2xh, and then you square the last thing. Okay, so that is f of x plus h. So then the limit as h goes to 0 of f of x plus h minus f of x all over h is given by the following. Limit as h goes to 0. F of x plus h is what we wrote above, x squared plus 2xh plus h squared all over h. And then we want to, that is f of x plus h. We want to subtract minus f of x, so minus x squared. Okay, so this part is f of x plus h, okay, and this part is f of x. And then we want to do equals the limit, and carry that limit over until you actually take the limit. Limit as h goes to 0 of x squared minus x squared are gone, so you're left with 2xh plus h squared divided by h, and this is the limit as h goes to 0 of, we can pull the h out from the top, so you get h 2x plus h divided by h, and the h's are gone, and you're left with the limit as h goes to 0 of 2x plus h. Okay. And now you can plug h equals 0, so h goes to 0, that's what the limit as h goes to 0 means, so you're left with 2x. That is your final answer. So the instantaneous rate of change of the temperature function x squared at time t x equals 2. Oh, so now we got to plug in x equals 2. So this is just for f of x. This is for all x. When x equals 2, then the instantaneous rate of change is 2 times 2. So we do that. Okay. Alternatively, you could have plugged the 2 in at the beginning as well, right here, and you would have gotten your final answer as 4. Okay, now let's look at secant and tangent lines. Okay, secant lines are lines that cut curves at 2 points, right? And tangent lines are lines that touch the curve at 1 point. Okay, exactly 1 point, and it matches exactly the steepness at that point. Okay, so think about this. What is slope? You know slope as y2 minus y1 over x2 minus x1, right? Where's that coming from? That's coming from 2 points, x1 comma y1 and x2 comma y2. Okay. Now if I told you the points were these 2 points right here, okay, so when the x value is x, the y value is f of x. Okay, from this point right here. When the x value is x plus h, this one, the y value is f of x plus h. Okay. So I have my 2 points here. So let me call this point 1 and point 2. So I have the slope m equals y sub 2 minus y sub 1 over x sub 2 is x plus h minus x sub 1, which is just x, and then the x's cancel out. Okay, so you're left with just f of x plus h minus f of x all over h. So the difference quotient is really nothing but the slope of the secant line. So we call this m secant. Okay? It's the slope of the secant line. What happens as, so you see this distance h here, right? What happens is h gets smaller and smaller. That is, x plus h gets closer and closer to x. Okay? So you can see that when that happens, this line, let's say, instead of looking between here and there, we're looking at between these 2 points. The line is going to go like this, and it's going to go like this, and it's just going to keep going until it becomes a single tangent line. Okay? And that's what happens when you take the limit as h goes to 0. The secant line becomes a tangent line as these two quantities, x and x plus h, approach each other. Okay? So the limit as h goes to 0 of the f of x plus h minus f of x is the slope of the tangent line. Okay? The slope of the tangent line is known as the derivative of the function. So this is where we are formally defining what the derivative is. It is the limit of the difference quotient. So let's do this example right here. The limit as, the limit and in my later videos I'm playing around with this new equipment that does these videos smoother, so hopefully all the files and programs I need will be downloaded, and then I'll be able to write the videos in the new system. Okay, so 2x squared, find the derivative. I'm sorry, here, let me erase this. The limit as h goes to 0 of f of x plus h minus f of x divided by h. Okay, the limit of the difference quotient is what we have above. So we need to find first f of x plus h. F of x plus h is 2x plus h. So every time you see x, you're going to plug in x plus h minus 9 x plus h plus 39. So this is 2. X plus h squared is x squared plus 2xh plus h squared. And then you multiply the 2, so we get, let's just close off this, minus 9x minus 9h plus 39. And then we can distribute this 2x squared plus 4xh plus 2h squared minus 9x minus 9h minus 39. Okay? So that is only f of x plus h. We need to find the limit as h goes to 0 of f of x plus h, which is this function right here, uh, 4xh plus 2h squared minus 9x minus 9h minus 39. Oops. Okay. Okay, 2x squared plus 4xh plus 2h squared. That is only f of x plus h. From that, you're going to subtract the original f of x. The original f of x is 2x squared. Oops. Minus 2x squared minus 9x plus 39. And then don't forget to put this in parentheses because it's all of x plus h, or all of x, f of x subtracted. And then when you distribute that 2, or that negative 2 rather, and then all over h. Okay. Okay, so then we get the limit as h goes to 0 of 2x squared. So this becomes minus 2x squared plus 9x minus 39. All the signs change. So then the 2x squared minus 2x squared is gone. 4xh is remaining. (2h squared). There's another 2h squared. The 9x minus 9x plus 9x are gone. And then the minus 39 plus 39 are gone. So you're left with 4xh plus 2h squared minus 9h all over h. Okay. And everything in the numerator has an h in it. That's what you want. Okay. So you want the limit as h goes to 0 of, pull out the h, and you get 4x plus 2h minus 9 all over h. And the h's are gone. Left with the limit as h goes to 0 of 4x plus 2h minus 9. When you plug h equals 0, you get 4x minus 9. Okay? That is the derivative of this function using the definition of the derivative. Let's review example 5 in our book. So this is on page 101. Okay. The following graph shows the annual sales of Apple Mac computers for recent years. Those sales are approximated by this function right here. Isn't that the function we just did? 2x squared minus 9x plus 39? Yep, sure is, right here. Whoops. Alright, so let us... Oops. Okay, so let us look at the example. So what is the instantaneous rate of change of this function at x equals 6 and x equals 1? And what is the instantaneous rate at x equals 6 and at x equals 1? Okay. So how would we find this? Well, first thing we need to do is take the derivative, which we did above, and you get 4x minus 9. And then you plug the 6 in, and you get 4 times 6 minus 9, which is 15. So 15 is, x equals 6 represents the year 2006, because here we're looking at years, we're looking at for recent years, right? Years since 2000. So when you plug 6 in, you get 15, so that represents 1.5 million units per year. So the growth rate is 1,500,000 units per year. Whereas when you plug 1 in, that represents 2001, and max sales were falling at a rate of 500,000 or 500,000 units per year. Okay. So what does differentiation, or what does the derivative tell us? It tells us the rate of change, how much something is growing or falling. Okay. If the derivative is positive, then the original function has positive slope. Oops. And it is increasing. Look at this example right here, right? So any kind of function, let me look at this example. Any kind of function, whether it's like this, or like increasing. So it has to look like this, or, yeah, right? So the original function has positive slope, okay, and it is increasing. If the derivative is negative, then the original function has negative slope and it is decreasing. Oops. E-A-S-I-N-G. So look at this function right here. So this is the function itself, and this is the derivative. Notice here how the function is increasing, so the derivative is positive. The function here is decreasing, so the derivative is negative. This part is still decreasing, so it's still negative, and then right here, where it becomes positive again. Okay, so these are the two points. Okay, points where it changes. Suppose a function is non-differentiable at certain points, meaning the derivative does not exist at those points. If the derivative does not exist, then we say the slope is undefined. Okay. So that is it. This was a fairly straightforward, fairly short rather, section. I want you to practice the differentiation or the difference quotient, okay, and limits. One more thing to say is that f prime of x is the notation, I believe it's Newton's notation, whereas this can also mean derivative, d over dx, okay? That's Leibniz's notation. So here are some problems for you to do, practice them. You can practice the even ones if you prefer to get the answers in the back, okay? We will do 2.3 next time.